Hi everyone, welcome again. Welcome to part 2, module 3. So far we have discussed how we can select a best model based on adjusted R square. That means higher adjusted R square, we'll looking for higher value of adjusted R square, lower value of MSE. MSE, that means value of estimated variance, that means S square, that means estimated sigma square, estimated value of sigma square. Or on other hand, this is the residual AMSE or residual standard error square, lowest of this square, or we're looking for lowest trace statistic. We'll be looking for Cm minus m is close to 0, and also looking for lowest AIC value. So this is the criteria we can select the best model we have discussed in module 1. Now in part 2 here, we'll discuss how we can select the best model. As I said, if we have so many independent variable, let's say in the previous example we have 3 independent variable, basically we have 8 models. Now the thing is that we know how we can select the best model based on the previous criteria. Now another way is how we can select the best model. That means which variable should be included. Either we need to select only X0 model or X0 X1 or X0 X2. Previously we have chosen X0 X2 or X0 X3, or which one. The first method is called the all possible regressions. The procedure involves fitting all regression equations formed by using one regressor, two regressor, and so on. That means one by one. Then select the subset of regressors as a best model based on appropriate criteria such as one of the discussed in the previous section. This process is cumbersome and requires a high-speed computer. For example, if we include X0 in all of the models and there are k other regressors, there will be 2 to the power k equations to be fitted. For example, in the previous example, we have 8 models. If k equal to 5, the number of equations should be, or the number of models should be 32. Because of the volume of computation involved in all possible regression procedures, it is often not economical even with a computer. For example, here we need to compute all of the 8 models, and we need to compute all of the criteria and then select the best model. So this is one option, but the next option is called backward elimination procedure. This procedure starts with all regressors in the model and then finds a good model by eliminating the regressor variables with no or very small effect on the response. So that means we include all in variable x0, x1, x2, x3, and then delete one by one. That variable has basically no effect on the response variable. Now under what criteria we'll remove the variable? The basis for elimination may be any statistic in the previous section, but usually the partial F statistic or AIC value. So that means based on AIC value, it will eliminate one by one, repeating this process until no further variables can be deleted without a statistically significant loss of fit. Another one is called forward selection. Forward selection, this procedure starts with fitting the model with only the intercept term in the model. An optimal subset is selected by adding the regressors one by one and checking the contribution of each model based on a statistic discussed in the previous section, but usually a statistic or AIC. So this is the opposite one. So it will include only X0 intercept model, and then it will include 1. If it is good, then it will include it there, and then it will include X2 if necessary. So 1 by 1 it will include variables in the model. Repeating this process until none involves the model to a statistically significant extent. The next one is called the stepwise regression procedure. The stepwise regression is similar to the forward. That means start with the intercept model procedure to start with. However, at every step, all regressors entered into the model are reassessed by using a backward elimination approach using F and AIC. It may be that a regressor added at an earlier step becomes redundant because of the relationship between it and the regressor now in the equation. So it will start, let's say, in the stepwise regression. Let's say it will enter with only the intercept model. If in the second step x1 is included in the model based on F and AIC, in the second step, when x2 will be included, it will also check whether x1, that means if we include x1 and x2, it would also check F and AIC, and x1 will be retained if the AIC value is still low. If AIC value will higher, then x1 will be removed from the model and we will include only x2. None of the procedures can in general guarantee the best subset regression model of any size. The order in which the regressors enter into the model or are eliminated from it does not necessarily indicate the importance of the regressor. The backward elimination, forward selection, and stepwise regression do not necessarily provide the same subset of regressors as the best model. So that means they can produce different results. Okay, so now I'm going to show you how we can use R, either use forward selection, backward elimination, or stepwise regression. Let's say if I go back to my R code here, so I'm using body fat data set. Here our variable is only x1, x2, and x3. Here is the command. So x1, x2, and x3, three variables here, and direction here is forward. If we make that step, so it will forward selection is that it will start with the intercept model, and then here are the other variables. It will include all of the variables. So look at how it works. So this is the forward selection. Look at here. This is the forward. So look at here. It start with only in the intercept model. Y1. So that is intercept model. And look at here. Here, first of all, the next model, either it will include x1 or x2. So x2 is highly significant. So in the next model, next step only included x2. So that means intercept plus x2. So look at here, and the AIC value is 38. In the next model only included x2, only x2. So that means x0 and x2. Now, if you include x2, next two variables are not significant. So that means that finally it will conclude that x a model that is only included x2. So x2 model is here. The coefficient of x2 is this, and in here is the beta 0. Beta 0 is negative 23.63, and x2 coefficient is 0.85. Because when x2 is included in the model, neither of these two variables are significant. This is the forward selection. What about the backward? Backward, it will start all of the variables x1, x2, x3, and then eliminate one by one. So if I run this one, look at here, what it will do is the backward one. So it at first it will include all of the variables x1, x2, x3. Now look at here, the highest insignificant variable is here in this case is 0.28. So that means this is the highly insignificant variable. In the next step, x2 will be eliminated. So that means in the next step only include x1 and x2. So if I go to the next step, and the AIC value here is 39.34. In the next step, look at only include x1 and x3. And if include x1 and x3, look at all of these two variables are significant. So in this case, the final selection should be x1 and x3, not x2. So look at the final selection is x1 and x3. And what about the stepwise? Stepwise method here again is similar to forward. Start with the intercept model, and we have x1, x2, x3, x2 and 3 variables, and test here, direction here is both. So look at how it works. So similar to forward, it will start with the intercept model first, and the next significant variable is x2. So in the next step, it will include the x2, x2, x2. It included the x2. It included the x2. So when x2 is included, the other variable here, none of these variables are significant. And not only that, when here x2 is included, it also tests the significance of x2. So that means if x2 is included here, it is still significant. So x2 will be taking in the model, but since none of the variables are statistically significant, probably the model will stop only taking x2. So in this particular example, forward and stepwise give us the same results, but backward elimination give us the different results. That's possible. So all of the methods may not produce the same results, but in this case, forward and stepwise produce the same results, but it may produce the different results as well. Okay, so now the next one here. So we have discussed forward selection, backward elimination, and stepwise regression procedure. Now we know the residuals, right? When the model is correctly fitted, the residual should be confirmed the assumption and should not expose any contradictions. Usually we are concerned about any possible violation of assumptions. You probably remember the assumption is that the constant variance, we call this homoscedasticity. Normality, that means normality, the residuals are normally distributed, and homoscedasticity, linearity. That means relationship between y and all of the explanatory variables are linear. We know the residual is there for any model, the observed value minus the fitted value, and this is the MSE. We know that MSE is the sum of squares of error divided by n minus p, and we use this as an unbiased estimate of the variance sigma square. We can easily calculate the residual. For example, in this particular case, since the model 3 included only x2 is the best model, in this case we would like to calculate the residuals. So what you can do, you can fit the model with y hat, is the y hat, and then for example in the first case the observed value is 13.28, first case value is 43.1, and the expected value, estimated predicted value is 13.28, and for the first observation the residual is 1.38. Or what you can do, you can directly calculate it from R. So model 3, so this is the model here. Now model 3 is the model here, and look at this is the model here, 20.23.85. so if I go back here, this is the model 3, our model 3 here, and then if we use that command RESIT summary of that model, we will get the residual. So first residual here is negative 1.38. so if we use R, you will get exactly you should get the same value, negative 1.38. look at negative 1.38 for the first case. So you can use R directly using that command to calculate the residual. Now look at the case here, the residuals here. So this is the residuals. We easily calculate this in R. We can also calculate standardized residual and standardized residuals. So one of them is DJ and another one is QJ. I'll show in a minute how we can do this in R. But what is standardized residual? Look at here. It is often more convenient to work with scale residuals, as scale residuals can convey more information than ordinary residuals. So this is the standardized residual. It is just EJ divided by MSE. That means EJ divided by S, where S is the unbiased estimate of sigma square. Standardized residuals have a mean of 0 and variance of approximately 1. Using standardized residuals allows us, for example, to identify outliers in the data relatively easily since they are like z-score. That is, we could define outliers if any of the standardized residual less than negative of 3 or greater than 3, then we can treat this as a outlier. So this is standardized residual. And another one is before that, another one is standardized residuals. But before that, we are discussing here hat matrix. Hat matrix is the relationship between fitted value y hat and the observed value y. So we know that in our model y equal to x beta. So that means y hat equal to x beta hat. This is our x, and this is our here. So this is our x beta hat. These are beta hat. So and then up to that value we call this Hayes. And Hayes here is a is called the hat matrix because it adds the hat y. The hat matrix has several useful properties. First of all, it is symmetric. That means Hayes transpose equal to Hayes. It is also idempotent. That means Hayes transpose Hayes equal to Hayes. Similarly, the matrix identity minus Hayes, where I is an n by n identity matrix, is symmetric and idempotent. The residuals can be expressed in terms of hat matrix because the residual is y minus y hat, so y minus x beta hat. And if we write this, then E equal to 1 minus Hayes y, where Hayes equal to this one. So now variance of E is sigma square 1 minus Hayes is I is the identity matrix. Because variance of y equal to sigma square I and I minus a is symmetric and idempotent, the matrix I minus a is generally not diagonal. So the residuals have different variance and they are correlated. So from this here we can calculate the variance for the ith residual is sigma square 1 minus Hayes I, and based on that, with this Hayes I value should be 0 to 1. Using MSE to estimate the variance of the residuals can directly overestimate of variance of EJ. Now, the standardized residual is QJ equal to EJ divided by variance or estimated variance of EJ. So that means EJ divided by square root of estimated variance sigma square 1 minus HJJ. And this is the we sometimes we write this here S. So sigma hat square equal to S square. So this is S. The standardized residuals do have approximately constant variance. That means this is 1. So we can easily calculate standardized residual. Standardized residual is just if you divide them by EJ divided by S, and we can also calculate standardized residual based on the hat matrix. The definition here is EJ divided by S square root of 1 minus HJJ. So first of all, we need to calculate this matrix, Hayes matrix first. Hayes matrix is the x transpose, x inverse, x transpose, and then diagonal element of Z will be using here in order to calculate the standardized residuals. So now look at here in this data set here, we how we can get DJ and QJ using R. So first of all, let's look at here. We already this is the residual, and if you just use that command R standard of that model, this will give you the standardized residual. For example, the first one here is negative of 6 1 approximately. If you go back there, standardized negative of 6 1. So that is, it is easy to calculate in R. And look at how we get the DJ. This is the standardized residual. So that means if we this is for in this particular example, if we divide for example, the first residual is 1.38, negative of 1.38, negative of 1.38. If we divide them, when negative of 1.38 divided by S, then we'll get the dj. And S is the, here is the MSE, that means unbiased estimate of sigma square. This is the model here. If with the sigma square hat, this is the MSE, and if we take the square root of that one, we'll get the first value. First value should be negative of 0.55, so negative of 0.55. On the other hand, you can directly calculate all of the standardized residual if we use that command. So residual summary, if we divide it by square root of MSE, you will get the standardized residual. So here is the all of the standardized residual here. So that means from this example, we can easily calculate all of the standardized residual, and standardized residual. Okay, so I have shown you how we can calculate all of these residuals here. So here, if you would like to use that one, so for example, let's say in this example, in that model, I will show you how we can calculate the Hayes matrix and then diagonal matrix. Let's say I should have that example in my R, so far I remember. So now, okay, yes. So our here is our model only x2. The hat matrix, can you remember the hat matrix is x transpose x inverse x transpose. So first of all, x0 is included here. So I have defined here x0, that means repeat of length of x2. And this is my x matrix. X matrix is the x0 and x2. Now, this is our hat matrix. So that means x is the multiplication of x transpose x inverse, solve is the x inverse, and then multiplication of x transpose. If I calculate that one, that will give me the hat matrix. And look at the diagonal element. First diagonal element is this. So this is the Hayes 1 1. This is Hayes 2 2. And this is the Hayes 3 3. So now look at with the calculation here. The Hayes 1 1 should be 0.17 and last one should be 0.05. If I go back to my R, look at here 0.07, that means 0.07, and what is the last one? Last one is 0.05. So this is the hat diagonal here. Now the standardized residuals for the first case. In the first case, this is the standardized the residual here, and we easily can calculate S. If you cannot, so let's say if I can calculate S here, S, that means if I calculate here, this one is the S value, that means this is basically model 2. Here is the model 2, yes. So, or what you can do, this is my MSE. If I run this one, and the square root of that is our S, so that means S should be SQRT of MSE. So that means S should be there 2.51. If I go back to here, so this is 2.51, and 1 minus Hayes JJ. If j equal to 1 for the first case is 0.17, is 0.17. If you calculate this will be 0.61. But we don't need to calculate each of this, because if we use the command here, in this command, it will give us the standardized residual for all of the observations. So this is the hat matrix here. But using, if you use R, just if you calculate the hat values here, this will give us your hat matrix. This is the first diagonal hat values. This is the hat values. So this is the first one, and this is the last one. and second one is 0.0536051. If you look at 0.05, so this is the second one here. So just in R, if you use the head values, you will get the head values. Okay, so we have shown here how we can calculate the residuals, standardized residual and standardized residuals. So now residual plots. So as we can remember, one of the most frequently used methods of checking the normality assumption of linear model is to use a normal probability plot. It is often called QQ plot. So our error term is normally distributed with mean 0 and variance sigma square. So if you use the QQ plot, the points of the plot should be approximately on a straight line if the errors are normal. So if we plot a QQ plot, and if this is the case, then the errors are normally distributed. Points are approximately on a straight line, indicating no violation of normality assumption. Now in R, if you use the QQ norm in R, then you will get the QQ plot. For example, let's say in that example we have included only, this is our model, we have included only x2. If you just use that command of that one, our standard BFQLM, this is our model here. So this is our QQ plot. Look at here, exactly normal if all the points lie on the straight line, but here is little bit different, but probably approximately normal. So this is the how we can check the normality using the QQ plot. Look at this one here. The curve is flat at both ends, indicative of shorter tail than the normal distribution. So in this case, normality assumption is violated. And look at the here, the upper end of the curve is upward moving, indicating positive skewness in the error distribution. And look at here, the lower end of the curve is downward moving, indicating negative skewness in the error distribution. So they are not normal. That means normal. If this is the case, then normality assumption violated. And look at this example here. The curve has sharp upward and downward turns at both extremes, indicating heavier tails than the normal distribution. Assumption of normality assumption in this case is not supported. The plots of residuals, even from a normal model, may not produce a perfectly straight line. It will be approximately straight only. So in our example, in the modified example, we included only x2 variable, and we can see our model is approximately normal. Another residual plot, residual versus fitted response. So that means residual versus fitted response. The plot of the residuals against fitted value of response is also used to detect violation of various model assumption. Look at this example here. If we this plot here, the plot appears to be horizontal band that contains all the points. No assumption is violated here. So that means constant variance assumption satisfied. In this plot, look at here, there is a looks like an upward moving band indicating of error in the analysis. The departure from the fitted equation is symmetric. The beta zero term may have been wrongly omitted from the model. It seems that there is a zero, model passing through the origin. Look at in this case, the plot forms a funnel-like shape, indicating that the variance of error term is not constant. The variance is an increasing function of y. An upward opening funnel will imply that the variance decreases as y increases. A transformation of y or a weighted least square analysis is needed, because here assumption is violated. And look at here, these two plots and then here indicate that the model is an inadequate. Some extra terms such as square or cross product may be missing, or transformation of y may be essential. So that means we need to transform y. In both cases, the linearity assumption is violated. That is, a non-linear model is appropriate. So if this is the case in the plot, then we can say that normality assumption is violated. Let's look at what happens in our case here. So is the residual versus y hat. So this is our residual and this is the fitted value of y. So if we plot here, look at here. So in our case model that has only x2 variable, we can see here this is completely random. So that means constant variance assumption is satisfied here in this particular example. But if this is any funnel shape or upward trend or downward trend, then we can say that constant variance assumption does not satisfy. And look at, this is the perfect plot. The plot has a double bow pattern which may occur when response is a okay. No, this, look at the case here. This is not perfect. So this is the case when the response is a proportion and hence has values between 0 to 1. So look at the response variables, like as if the response variable y is value is between 0 to 1, this may happen here. This indicates that the variance of binomial proportion for p equal to 0.5 is larger than closer to 0 or 1. Needs suitable transformation for y or the regressor. So if this is the case here, then it may be the case that the response variable y is proportion, and if this is the case, we need to transform y. That means variance, constant variance assumption does not satisfy. In some cases, if we have a time series data set, the plot of residuals against time is used to check model assumptions. When the pattern of a plot reassembles a funnel shape graph, then the assumption of constant variance is in doubt. The time sequence plot of residuals may also indicate possible autocorrelation, that is, the errors at one time point are correlated with those at another time points. The problem of autocorrelation is beyond the scope of this course, so it is sufficient to say that this usually indicates an important regressor has been omitted from the model. So we are not dealing with the correlation in this course. So if this is the case here, look at if the autocorrelation exists in the data set, look at here. Here the first one here is the positive autocorrelation, and the second one here is the negative autocorrelation. However, we are not discussing autocorrelation in this course, but this is the case that if we calculate the residuals, and if the residuals terms are correlated, then we can say that the problem of autocorrelation. So this is just the autocorrelation. But if you do other courses, like as in advanced statistical models, in those courses we usually discuss the problem of autocorrelation. If this is the case, so that means if the constant variance assumption is not satisfied, we can transform y in different situation to achieve the constant variance. So first of all, if sigma square, that means error variance, is proportional to expected value of y, that means mean, in that case that response variable y is possibly count data. If it is a count data, then this follows Poisson distribution. In this case, we need to use this transformation. If the relationship between error variance and expected value of y is something like this may be the case that your response variable like a 0 or 1 binomial. In that case, we need to use this transformation. If the relationship between these, that means in that case the response variable might be positive continuous. In this case, we need to use that type of transformation, that means log of y. If the relationship is something like this, we need to use either this transformation or this transformation. On the other hand, if the relationship again this, then again the response variable can be either 0 or 1. In this case, we need to use that type of transformation. Okay, so this is the second part of module 3, and we have another recordings for part 3 of module 3.